Right now, without feeling a thing, you're moving through one of the strangest places in the known universe. You're not standing on solid cosmic ground. You're inside a vast emptiness, a colossal hollow in space, so large it stretches nearly 2 billion light-years across. This is not science fiction, and it is not a metaphor. Astronomers have discovered that our galaxy, our local neighborhood, and everything we can easily observe sits inside a gigantic cosmic depression where matter is missing. Not a little missing, but enough to fundamentally change how space itself behaves. This region is known as the KBC void, a name that sounds harmless, almost technical, yet it describes a structure so extreme that it quietly threatens some of our most trusted ideas about the universe. Inside this void, the density of matter is roughly 20% lower than what cosmology predicts should exist. That absence may not sound dramatic, but on cosmic scales, it is enormous. Matter shapes gravity, gravity shapes motion, and motion is how we measure reality. If matter is missing, gravity weakens. If gravity weakens, everything we measure, from the speed of galaxies to the age of the universe itself, begins to shift. Astronomers have long puzzled over why the universe appears to be expanding faster near us than it does when measured across the deep cosmos. This contradiction has become one of the biggest crises in modern cosmology. The unsettling possibility is that the universe is not behaving strangely at all. We are, or more precisely, our location is. Measuring the cosmos from inside a massive void may be like trying to understand Earth's climate while standing inside a hurricane. The numbers make sense locally, but they do not reflect the true global picture. If this is correct, then the foundations of cosmology remain intact, but our perspective is deeply biased. And if it is wrong, then the universe is hiding something even stranger. Either way, this invisible hole surrounding us forces a single uncomfortable question. What if the universe we think we know is an illusion created by where we happen to be standing? If this void were only an idea, it could be dismissed as speculation. But it was uncovered the most unromantic way science ever reveals something unsettling: by counting. In 2013, 3 astronomers set out to do what seemed like a routine task. Ryan Keenan, Amy Barger, and Lennox Cowie were mapping the distribution of galaxies around our cosmic neighborhood, using data from multiple deep sky surveys. They analyzed the positions and distances of roughly 35,000 galaxies, extending outward across billions of light-years. The goal was simple: compare how many galaxies exist near us to how many should exist according to standard cosmology. What they found was anything but simple. Everywhere they looked in the nearby universe, galaxies were missing. Not a few. Not an amount that could be blamed on measurement error. Roughly 20% of the expected galaxies were gone. At first, the team assumed a mistake. Astronomers are trained to distrust extraordinary results. They rechecked distances, recalibrated instruments, and compared independent data sets. The deficit remained. As they expanded their analysis outward, a pattern emerged. The missing galaxies were not confined to one direction. The shortage extended outward in every direction from Earth, forming a vast, roughly spherical region of underdensity. The scale was staggering. This region stretched nearly 1 billion light-years from side to side, placing our galaxy uncomfortably close to its interior. This was not a gap between clusters or a statistical fluctuation. It was a coherent structure, large enough to challenge the assumption that the universe becomes smooth when viewed on sufficiently large scales. To rule out coincidence, the team compared results from multiple galaxy surveys, each using different instruments, methods, and sky coverage. Every independent check pointed to the same conclusion. The local universe is missing matter. The paper describing this structure gave it a technical name derived from the author's initials, the KBC void. But there was nothing technical or trivial about its implications. A void of this size should be extraordinarily rare. Its existence was not just another catalog entry. It was a warning sign that something fundamental about our cosmic surroundings had been overlooked. The discovery immediately ran headfirst into one of the most trusted assumptions in cosmology. According to the standard model of the universe, matter should even out when viewed on large enough scales. Galaxies may cluster, leaving smaller gaps between them, but those irregularities are supposed to fade as you zoom farther out. The universe, in theory, becomes statistically smooth. The KBC void does not fit that picture. A region nearly 2 billion light-years wide with a 20% deficit of matter is not a gentle fluctuation. It is a structural anomaly. When cosmologists turned to computer simulations based on the standard model to see whether such a void could naturally arise, the results were deeply uncomfortable. In thousands of simulated universes, structures like the KBC void almost never appeared. When they did, they required extremely rare initial conditions, the kind of statistical outliers scientists usually expect to see nowhere at all. Some calculations placed the odds of forming a void this large and this empty at less than 1 in 1,000. Others went further, describing it as a 10 sigma deviation from the cosmic average, a level of improbability so extreme that it borders on impossible within the observable universe. Yet the void is there. We are inside it. This forces a question cosmologists are reluctant to ask because of how destabilizing it is. If the universe is supposed to look the same from any location, what happens if our location is not typical? Nearly every measurement we make relies on the assumption that our cosmic vantage point is ordinary. We measure galaxy speeds, distances, and expansion rates as if our surroundings represent the universe as a whole. But if we live inside an enormous underdense region, that assumption collapses. Gravity behaves differently in emptier space. Motions accelerate. Distances stretch in unexpected ways. What looks like a universal truth may be nothing more than a local illusion. And if that is the case, then the problem is no longer a strange void. The problem is everything we think we know about the universe, measured from a place that was never average to begin with. This uncomfortable realization leads directly to one of the most serious problems in modern cosmology, the Hubble tension. For decades, astronomers have tried to pin down how fast the universe is expanding, a value known as the Hubble constant. Two methods, both extraordinarily precise, should agree. One looks far back in time, using the faint afterglow of the Big Bang to infer how the universe expanded from its earliest moments to today. The other measures the nearby universe directly, timing how fast galaxies are moving away from us right now. But they do not agree. The difference is not subtle. The numbers diverge by about 9%, far beyond the margin of error. In cosmology, this is not a minor discrepancy. It is a crisis. Every refinement to the measurements has only sharpened the disagreement, not erased it. If both methods are correct, something fundamental is missing from our understanding. This is where the void re-enters the story. If our galaxy sits inside a massive underdense region, gravity does not pull on surrounding galaxies the way it would in a typical part of the universe. Instead, the denser matter outside the void exerts a net gravitational pull outward. Galaxies inside the void are effectively being tugged away from the center, gaining extra velocity on top of the normal cosmic expansion. To an observer inside the void, This motion is indistinguishable from faster expansion. The universe appears to be stretching more rapidly nearby than it truly is on average. This means the local measurement of the expansion rate is inflated, not because the universe behaves differently here, but because our position distorts the view. The deeper, more distant measurements see the broader universe and return a lower value. Suddenly, the conflict makes sense. The numbers do not disagree because one is wrong. They disagree because they are answering different questions from different locations. The most unsettling conclusion is also the simplest. We are not measuring the universe incorrectly. We are measuring it from the wrong place. Once the idea of a local void enters the picture, the physics inside that region takes on a very different character from the universe we usually imagine. A cosmic void is not a hole in the sense of absolute nothingness. It still contains matter, but far less of it. Thin wisps of hydrogen gas drift through the darkness. Dark matter is present, though diluted and spread across enormous volumes. And dark energy, the most mysterious component of the cosmos, fills the void just as it fills every other region of space. What changes is the balance of power. Gravity depends on matter, and inside a void, matter is scarce. With less mass to pull things together, gravity weakens dramatically. This has profound consequences. In dense regions of the universe, gravity sculpts structure, drawing galaxies together into groups, clusters, and superclusters. In a void, that process effectively stalls. There is simply not enough gravitational attraction to assemble new large-scale structures. No rich clusters form. No massive filaments emerge. The void remains a void, frozen in an underdeveloped state. As gravity fades into the background, another force steps forward. Dark energy, which acts as a kind of pressure built into space itself, becomes dominant. In regions packed with matter, gravity partially counteracts dark energy, slowing the local expansion of space. Inside a void, that resistance nearly vanishes. Dark energy wins the contest outright. As a result, voids expand faster than the universe on average. They swell outward like bubbles in a cosmic foam, pushing against the denser walls of galaxies that surround them. This expansion is not subtle. Galaxies inside a void are not merely drifting apart. They are being accelerated outward by the gravitational imbalance between the empty interior and the heavier matter concentrated beyond the void's edges. From the inside, it feels as though galaxies are being pushed away from the center at extraordinary speeds, hundreds of thousands of miles per hour. This motion is not caused by dark energy pushing directly on galaxies, but by gravity pulling more strongly from outside the void than from within it. The effect reshapes how light travels through these regions. When light passes through normal space, it is subtly influenced by gravitational fields along the way. Inside a void, those fields are weaker. Photons lose and gain less energy as they move through the shallow gravitational landscape. This leaves detectable fingerprints on our observations. One of the most important appears in the cosmic microwave background, the ancient radiation left over from the early universe. As this light crosses a large void, it experiences what is known as the integrated Sachs-Wolf effect. Because the void is expanding while the light passes through it, the tiny energy changes the photons' experience do not cancel out perfectly. The result is a slight cooling of the radiation, showing up as faint temperature depressions in the cosmic microwave background. These effects are small, measured in millionths of a degree, but they are real, and they line up with the locations of large voids seen in galaxy surveys. The same physics that accelerates galaxies outward also alters how we interpret distances, redshifts, and expansion rates. Inside a void, motions that would normally average out across space instead align in the same outward direction. This amplifies local measurements and makes the universe appear to behave differently than it does on truly cosmic scales. For cosmologists, this transforms voids from empty curiosities into powerful tools. In dense regions, gravity complicates nearly every measurement. In voids, gravity retreats, leaving dark energy exposed. These vast, underdense regions become natural laboratories where dark energy's influence can be studied with fewer competing effects. By observing how voids expand, how galaxies move within them, and how light is altered as it passes through them, scientists gain one of the clearest windows available into the force that now dominates the universe's fate. The emptiest places in the cosmos may be the best places to understand the force that is tearing the cosmos apart. Understanding what happens inside a void only makes sense once you zoom out far enough to see how voids fit into the larger design of the universe. On the grandest scales, the cosmos is not a smooth ocean of evenly scattered galaxies. It is a vast, intricate structure that resembles Swiss cheese on a cosmic scale. Dense regions form walls and filaments, long strands of matter stretching across hundreds of millions of light-years. Where these filaments intersect, knots appear, massive hubs where galaxy clusters crowd together. Between them lie the voids, enormous hollow regions that dominate the universe by volume while containing very little mass. This is the cosmic web, the true architecture of everything we see. It is counterintuitive, but most of the universe is empty. Roughly 90% of cosmic volume is made up of voids, while the remaining 10% holds nearly all the matter. Galaxies, stars, planets, and people exist in a thin scaffolding draped around immense expanses of darkness. For much of the 20th century, this structure remained hidden. Early astronomers saw only flat projections of the sky. Galaxies appeared scattered randomly across the celestial sphere, giving the impression of a roughly uniform universe. Distance was the missing ingredient. Two galaxies that looked adjacent on the sky could be separated by billions of light-years along our line of sight. It was not until astronomers began systematically measuring redshifts that the three-dimensional shape of the universe snapped into focus. Redshift surveys has revealed how fast galaxies were moving away from us, which allowed scientists to calculate their distances. As these surveys grew larger in the 1970s and 80s, patterns began to emerge. Galaxies were not evenly distributed. They traced out sheets and filaments, enclosing vast, empty regions. The picture sharpened dramatically with the arrival of large digital surveys. The Sloan Digital Sky Survey, which began around the turn of the millennium, mapped millions of galaxies across a huge swath of the sky. For the first time, astronomers could see the cosmic web in stunning detail. Filaments twisted and branched like blood vessels. Walls stretched across space like cosmic membranes. Voids appeared as dark bubbles, some hundreds of millions of light-years wide. Among the most striking discoveries were colossal superstructures that pushed the limits of what cosmology expected. The Sloan Great Wall, a filamentary structure nearly 1.5 billion light-years long, stood out as one of the largest coherent features ever observed. On the opposite extreme were supervoids, regions so empty and so vast that they seemed to defy probability. These discoveries forced a conceptual shift. Galaxies were no longer seen as the fundamental units of cosmic structure. They were markers, glowing beads strung along an invisible framework of dark matter and gravity. The web itself was the real structure, shaped by the growth of tiny density fluctuations into a sprawling network over billions of years. Gravity pulled matter into filaments and nodes, while dark energy drove the expansion of the voids between them. Seen this way, the universe is not dominated by galaxies, but by the spaces between them. This perspective changes how we interpret almost every observation. When we look at a cluster of galaxies, we are seeing a bright knot in the web. When we look into a void, we are peering into the dominant environment of the cosmos. The Milky Way and its neighbors sit on one strand of this vast network, bordering regions of near emptiness that stretch far beyond our imagination. The cosmic web is not static. Over time, filaments grow thinner as matter drains into clusters, and voids expand as dark energy accelerates their growth. The contrast between dense and empty regions increases, sharpening the web structure. In this evolving landscape, galaxies are passengers rather than architects, carried along by forces far larger than themselves. What appears to us as a universe filled with galaxies is, in truth, a universe defined by absence. The stars and galaxies we see trace the edges of something much larger and darker. The cosmic web is the skeleton of reality, and the voids are not gaps in that skeleton. They are its dominant feature. To understand why the cosmic web looks the way it does, with its vast empty regions dominating space, we have to rewind all the way back to the universe's earliest moments. Shortly after the Big Bang, the universe was not the structured place we see today. It was an extremely hot, dense sea of particles and radiation, expanding rapidly. Yet even in that early chaos, the universe was not perfectly smooth. Tiny quantum fluctuations, born from the uncertainty inherent in quantum physics, introduced minuscule variations in density. These differences were unimaginably small, on the order of 1 part in 100,000, far too subtle to notice directly. But gravity has a remarkable property. It amplifies even the slightest imbalance over time. Regions that began just a little denser than average exerted a slightly stronger gravitational pull, drawing in more matter from their surroundings. As they gained mass, their gravity increased, pulling in even more material in a runaway process. These regions eventually became the seeds of galaxies, galaxy clusters, and the dense knots and filaments of the cosmic web. At the same time, the opposite process unfolded elsewhere. Regions that began slightly less dense than average lost matter to their denser neighbors. As material flowed outward, these underdense regions became emptier still. Gravity, instead of pulling matter inward, effectively drained these regions, allowing them to expand faster than their surroundings. Over hundreds of millions of years, these subtle differences were stretched and exaggerated by cosmic expansion, transforming faint quantum ripples into enormous voids spanning hundreds of millions and eventually billions of light years. This process, known as gravitational instability, is the engine that built the universe's large-scale structure. It turned microscopic irregularities into the grand architecture we observe today. As time passed, dense regions collapsed into increasingly complex structures, while underdense regions grew larger and more dominant in volume. The result is a universe where matter occupies a relatively small fraction of space, gathered into filaments and clusters, while emptiness fills the rest. Today, voids account for roughly 90% of the universe's volume, even though they contain only a small fraction of its mass. The universe we inhabit is not defined by where matter is abundant, but by where it is missing, and that absence traces its origin back to the smallest quantum fluctuations at the dawn of time. Knowing how voids form makes the next realization far more unsettling, because the KBC void is not a distant curiosity. It is our address. The Milky Way is not floating somewhere near the edge of this vast emptiness, nor are we sitting safely outside it, looking in. Measurements place our galaxy well inside the void, roughly 200 to 400 million light-years from its center. On human scales, that distance is incomprehensibly large, on the scale of a structure that stretches nearly 1 billion light-years in every direction. It is relatively small. We are embedded deep enough within the underdense region that its physical effects surround us from all sides. This position alone is enough to influence nearly every large-scale measurement we make about the universe. Our galaxy belongs to the local group, a modest collection of around 80 galaxies dominated by the Milky Way and Andromeda. The local group, in turn, is part of a far larger structure known as the Laniakea supercluster, an immense region containing on the order of 100,000 galaxies spread across more than 500 million light-years. By everyday astronomical standards, Laniakea is enormous. It defines the gravitational basin that governs the motion of our galaxy and its neighbors. Yet even this colossal supercluster exists within the KBC void. This is where intuition begins to fail. How can a structure containing 100,000 galaxies still count as part of an underdense region? The answer lies in scale. The void is not defined by the complete absence of matter, but by a deficit relative to the cosmic average when measured across truly vast volumes. Laniakea is a concentration within a much larger emptiness, like an island rising from a shallow cosmic sea. The void is so large that it easily contains entire superclusters without ceasing to be underdense overall. Our position inside this structure has measurable consequences. The Milky Way is not merely carried along by cosmic expansion. It has a substantial peculiar velocity, meaning a motion caused by local gravitational forces rather than the stretching of space itself. Relative to the rest frame of the universe defined by the cosmic microwave background, our galaxy is moving at roughly 600,000 miles per hour. This is not a trivial drift. It is a clear signal that powerful gravitational gradients exist in our local environment. Much of this motion can be traced to the imbalance created by nearby voids. The local void, a smaller underdense region adjacent to our position and connected to the larger KBC void, contributes significantly to this effect. With less matter pulling from one direction and more matter pulling from others, our galaxy is effectively being accelerated away from emptiness toward denser regions of the cosmic web. This motion is layered on top of other gravitational influences, such as the pull of the Virgo cluster and the broader flows within Laniakea itself. When astronomers map galaxy motions across hundreds of millions of light-years, they find something even more striking. Entire regions of space are moving coherently in the same direction, creating large-scale bulk flows. According to the standard model of cosmology, these flows should diminish as you average over larger volumes. Random motions ought to cancel out, leaving only small residual velocities. Observations do not show that. Instead, bulk flows extending out to 200 or even 300 million light-years exhibit speeds far higher than predicted. These flows are not random. They align with the structure of the KBC void, pointing away from its interior toward denser surrounding regions. In other words, galaxies across vast expanses are responding to the same gravitational imbalance. This behavior is extremely difficult to explain if our region of the universe were typical. It becomes far more natural if we are inside a massive underdense bubble. The void creates a large-scale velocity field that affects everything within it, from small galaxy groups to superclusters. Our galaxy's high speed is not an anomaly. It is a symptom. The implication is profound. We are not passive observers watching the universe from a neutral location. We are moving through a dynamic gravitational landscape shaped by the emptiest structures in existence. Our measurements of distance, motion, and expansion are all taken from inside this environment. The KBC void is not just a background feature. It is an active participant in our cosmic story, quietly shaping what we see and how we interpret the universe. Once we recognize that we are embedded inside a vast, underdense region and moving through it at extraordinary speed, a troubling consequence follows. Almost everything we know about the universe comes to us on beams of light, and that light does not travel through empty, neutral space. It moves through a gravitational landscape. When light passes through dense regions filled with matter, its energy, wavelength, and timing are subtly altered by gravity. Inside a void, that landscape changes. With less matter to bend spacetime, photons experience weaker gravitational effects along their journey. Over hundreds of millions or billions of light years, those small differences accumulate. The result is that light reaching our telescopes from distant galaxies carries the imprint of the void it passed through. This alone would be manageable if the effect were random, but it is not. Because we sit inside a coherent, spherical, underdense region, the distortions all point in the same direction. They bias our observations systematically rather than canceling out. This becomes critical when we measure cosmic expansion. The most direct way to measure how fast the universe is expanding nearby relies on observing objects of known brightness, such as certain types of exploding stars, and comparing how bright they appear to how fast they are receding from us. That recession speed is inferred from redshift, the stretching of light as space expands. But redshift does not distinguish between expansion caused by the universe as a whole and motion caused by local gravitational flows. Inside a void, galaxies are not just carried apart by expansion. They are being accelerated outward by the gravitational pull of denser matter beyond the void's edges. To an observer inside the void, this extra motion looks exactly like faster cosmic expansion. The measurement is not wrong in a technical sense. It is faithfully recording what is happening locally. The problem is that the local environment is not representative of the universe as a whole. The expansion rate we infer nearby is inflated by the void's velocity field. This provides a remarkably natural explanation for the Hubble tension. When astronomers measure the expansion rate using nearby objects, they are probing space well inside the KBC void. Their results consistently point to a higher value. When they measure the expansion rate using methods that rely on the distant universe, such as the cosmic microwave background or very remote galaxies, the light has traveled mostly outside the void. Those measurements reflect the broader cosmic average and return a lower value. The discrepancy is not a contradiction between experiments. It is a mismatch between environments. This idea leads to a powerful and testable prediction. If the void is responsible for inflating local measurements, then the inferred value of the Hubble constant should depend on distance. Very nearby measurements should give the highest values because they are most affected by the void's outflow. As observations extend farther out, sampling regions closer to the void's edge and beyond it, the measured expansion rate should gradually decline toward the true cosmic value. For years, this prediction was difficult to test because precise distance measurements become harder as objects grow fainter and more distant. But as data has improved, a pattern has begun to emerge. Studies that group supernova measurements by distance find exactly this trend. The Hubble constant appears higher when inferred from the closest supernovae and decreases as more distant explosions are included. The transition occurs on scales of roughly 2 billion light-years, suspiciously close to the estimated size of the KBC void. Beyond that scale, The inferred expansion rate stabilizes near the lower value predicted by early universe measurements. This phenomenon has become known as the Hubble bubble, a region of space within which expansion appears anomalously fast. The term is evocative, but the implication is unsettling. It suggests that our most precise local measurements are biased not by experimental error, but by geography. We are trapped inside a bubble that distorts our view of the cosmos. Correcting for this bias is not straightforward. We cannot simply step outside the void and take measurements from a more typical location. We must rely on light that has traveled immense distances, carrying the integrated history of its journey through different cosmic environments. This makes cosmology far more subtle than a simple reading of numbers on a chart. The Hubble bubble hypothesis does not eliminate all tension or answer every question, but it reframes the problem in a profound way. Instead of demanding new particles, exotic forces, or radical changes to fundamental physics, it asks us to confront a simpler possibility. The universe may be behaving exactly as our theories predict. The mismatch arises because we are observing it from a place that is anything but average. Our cosmic address matters. The emptiness surrounding us stretches space, accelerates galaxies, and alters the light we use to measure reality. What we call a crisis in cosmology may, in fact, be a crisis of perspective. If the Hubble bubble interpretation is correct, its implications do not stop at a single disputed number. The expansion rate of the universe is a keystone parameter in cosmology, and when that stone shifts, everything built upon it trembles. The value of the Hubble constant feeds directly into our estimates of the universe's age, the behavior of dark energy, and the timeline by which cosmic structures formed. A faster expansion rate implies a younger universe. A slower one implies an older cosmos. This is where the tension deepens into a genuine crisis. According to measurements based on the cosmic microwave background, the universe is about 13.8 billion years old. That estimate is remarkably consistent across different analyses and is supported by a well-tested framework describing how the universe evolved from its earliest moments. But if the higher expansion rate measured locally were truly universal, the universe would be significantly younger, closer to 12.7 billion years old. That difference may sound small, but it collides head-on with another line of evidence that is difficult to dismiss. The oldest stars in our galaxy appear to be nearly 13 billion years old. These stars, found primarily in ancient globular clusters, are cosmic fossils. Their ages are determined by well-understood principles of stellar physics, including how quickly stars burn through their nuclear fuel and how they evolve over time. Multiple independent methods converge on the same conclusion. Some stars are almost as old as the universe itself. If the universe were younger than its oldest stars, the timeline would be physically impossible. This contradiction is one of the sharpest blades cutting into the heart of modern cosmology. It suggests that at least one of our assumptions is wrong, and possibly more than one. One possible resolution is the simplest conceptually, but the most unsettling philosophically: void bias. If we live inside a massive underdense region that inflates local measurements of the expansion rate, then the higher Hubble constant does not reflect the universe as a whole. In that case, the older age derived from the cosmic microwave background remains correct, and the apparent conflict with stellar ages disappears. The universe is old enough for its oldest stars, and the crisis dissolves into a problem of perspective. This explanation preserves most of the standard cosmological model, but it comes at a cost. It requires accepting that our location in the universe is unusually special, a conclusion that runs against the long tradition of removing humanity from any privileged cosmic position. Another possibility shifts the blame away from location and toward the nature of dark energy itself. In the standard LCDM model, dark energy is represented by a cosmological constant, a fixed property of space that does not change over time. But what if that assumption is wrong? If dark energy has evolved, growing stronger in the recent universe than it was in the past, it could reconcile the measurements. The early universe, observed through the cosmic microwave background, would expand more slowly, producing an older universe. The late universe, measured locally, would expand faster, producing a higher Hubble constant. This idea is elegant in its way, but it introduces new complications. A changing dark energy component requires new physics beyond the standard model, and any such modification must fit an enormous body of existing data. So far, no evolving dark energy model has managed to solve the Hubble tension without creating new conflicts elsewhere. A third possibility is far less exotic, but equally frustrating: systematic measurement error. Perhaps one or more of the techniques used to measure cosmic expansion contain subtle biases that have not yet been fully accounted for. Dust between galaxies might dim distant supernovae more than expected, making them appear farther away and artificially boosting the inferred expansion rate. The stars used as cosmic distance markers might behave slightly differently depending on their environment, introducing hidden errors. These ideas are actively tested, and over time, many have been ruled out or tightly constrained. The problem is that the measurements on both sides of the Hubble tension are extraordinarily precise, and improving their accuracy has only made the discrepancy more pronounced. The margin for hidden error is shrinking. This has pushed some researchers toward more radical explanations, including modifications to gravity itself. The most well-known alternative is modified Newtonian dynamics, or MOND. Originally proposed to explain the unexpected rotation speeds of galaxies without invoking dark matter. In its original form, MOND alters how gravity behaves at extremely low accelerations, strengthening it compared to standard gravity. While MOND struggles to explain many cosmological observations on its own, extensions of the idea have been developed that operate on larger scales. In these frameworks, gravity becomes more effective in low-density environments, exactly the conditions found in cosmic voids. This has an intriguing consequence. Structure forms more efficiently. Voids become larger and deeper. Superclusters become more pronounced. Features like the KBC void no longer appear as improbable anomalies, but as natural outcomes of cosmic evolution. In such models, the statistical unlikelihood of our environment vanishes. However, modified gravity theories face serious challenges. General relativity has passed every experimental test to extraordinary precision, from the bending of light by massive objects to the behavior of gravitational waves. Any alternative theory must reproduce all of these successes while also explaining the Hubble tension and large-scale structure. So far, no modified gravity model has achieved that balance without introducing its own inconsistencies. This leaves cosmology in an uncomfortable position. The standard LCDM model remains enormously successful, accurately describing the cosmic microwave background, the distribution of galaxies, and the formation of structure across vast scales. Yet it struggles with a handful of increasingly significant anomalies. The void bias explanation preserves the model, but challenges a foundational philosophical assumption. Evolving dark energy introduces new physics that lacks independent confirmation. Measurement errors grow harder to defend as techniques improve. Modified gravity offers elegant solutions to some problems, but stumbles on others. None of these paths is fully satisfying. And that is what defines a true scientific crisis. The debate is ongoing, and it is far from settled. New surveys are mapping the universe with unprecedented depth and precision. Future observations will push beyond our local cosmic neighborhood and test whether the Hubble tension persists at ever greater distances. If the discrepancy fades, the void explanation will gain strength. If it remains, even outside the influence of local structure, more radical revisions may be unavoidable. For now, cosmology stands at a crossroads. The emptiness surrounding us may be a cosmic coincidence, a bias of perspective that we must learn to correct, or it may be a clue pointing toward deeper truths about gravity, dark energy, and the structure of reality itself. Either way, the KBC void has transformed a numerical disagreement into a fundamental question about how we understand the universe and whether the model that has guided us for decades is complete or only an approximation of something far stranger. As the debate over models and parameters continues, there is one class of observations that refuses to stay quietly in the background. These are not subtle statistical discrepancies or abstract inferences drawn from ancient light. They are motions. Real, measurable motions of galaxies across vast stretches of space. When astronomers chart how galaxies move relative to the expanding universe, they find patterns that are difficult to reconcile with a smooth, homogeneous cosmos. These motions, known as bulk flows, reveal that entire regions of space are drifting together in coherent directions, as if responding to a force far larger than any single cluster or filament. The scale of these flows is immense. They extend across hundreds of millions of light-years, far beyond the range where standard cosmology predicts such coordinated motion should survive. In a universe that is statistically uniform on large scales, local gravitational pulls from clusters and superclusters should average out as you look farther and farther away. Random motions cancel. Order dissolves into noise. Yet observations stubbornly show the opposite. Large volumes of the universe appear to be moving together, flowing away from underdense regions and toward denser ones in a pattern that defies simple explanation. This is not a new discovery, but it has become more difficult to ignore as data has improved. Surveys that measure galaxy velocities using a variety of techniques, including distance indicators independent of redshift, consistently detect bulk flows with amplitudes larger than expected. Some of these flows persist out to scales of 200 or even 300 million light-years. The directions of motion are not random. They align with known features of large-scale structure, including major voids and superclusters. In a perfectly homogeneous universe, governed strictly by the standard LCDM model, such flows should be exceedingly rare. When simulations are run under those assumptions, large-scale motions tend to die out beyond about 100 million light-years. The real universe refuses to cooperate. This mismatch has been a lingering source of discomfort for cosmologists, often treated as a statistical fluke or an artifact of limited data. But when viewed through the lens of the void model, these motions take on a different meaning. Inside a massive underdense region like the KBC void, gravity does not balance symmetrically. Matter is missing from the interior, while it accumulates in the walls and filaments surrounding the void. This creates a large-scale gravitational gradient that extends across the entire structure. Galaxies inside the void are not just expanding away from one another. They are being pulled outward toward the denser regions beyond the void's boundary. The result is a coherent velocity field, a cosmic outflow that spans the full diameter of the void. From this perspective, bulk flows are not anomalies. They are expected. They are the natural dynamical response of matter embedded in an enormous underdense environment. The larger the void, the larger and more coherent the flow. The KBC void, with its billion light-year scale, is more than capable of generating the observed motions. This interpretation gains further weight when we consider our own galaxy. The Milky Way is not at rest with respect to the cosmic microwave background, the radiation that defines the universe's large-scale reference frame. Instead, it is moving at roughly 600,000 miles per hour relative to that background. This motion is not fully explained by the gravitational pull of nearby structures alone. The Virgo cluster, the Great Attractor, and other dense regions contribute, but when their influence is carefully modeled, a significant residual velocity remains. That residual points away from nearby underdense regions and aligns with the larger void environment. In other words, part of our galaxy's motion appears to be driven not by what is nearby and massive, but by what is nearby and empty. This is a deeply counterintuitive idea. We are accustomed to thinking of gravity as a force exerted by mass, not by absence. But in a universe shaped by gradients in density, emptiness matters. Where matter is missing, gravitational pull is weaker, and that imbalance creates motion just as surely as the presence of mass does. The Milky Way's velocity is therefore not just a number. It is a clue. It encodes information about the large-scale distribution of matter around us, including the voids that dominate cosmic volume. When cosmologists include large voids in their models, the predicted velocities of galaxies increase and align more closely with what is observed. Bulk flows become less mysterious. The peculiar velocity of the Milky Way becomes less anomalous. The universe begins to look less like a smooth, expanding fabric with minor wrinkles and more like a dynamic landscape shaped by vast regions of absence as much as by concentrations of mass. This does not mean the standard model is entirely wrong. On many scales, it works extraordinarily well, but it does suggest that one of its simplifying assumptions, large-scale homogeneity, may be more fragile than once believed. If the universe takes longer to smooth out than expected, or if large voids are more common than simulations predict, then bulk flows are not statistical accidents. They are signatures of a cosmos that is more structured and more uneven than our idealized models assume. The implications extend beyond galaxy motions. Velocity fields influence how structures grow, how clusters form, and how matter streams along filaments of the cosmic web. They affect the interpretation of redshift surveys and the calibration of distance indicators. They even feed back into the Hubble tension because coherent flows add to or subtract from the apparent expansion rate depending on direction and distance. In a void-dominated environment, these effects do not average away quickly. They persist across enormous distances, biasing measurements in subtle but systematic ways. Critics of the void model argue that bulk flow measurements are difficult and prone to uncertainty. Distances are hard to measure precisely, and errors can propagate into velocity estimates. This is true, and it is why the debate remains active rather than settled. But what has shifted in recent years is not just the quantity of data, but its consistency. Independent surveys using different methods repeatedly find flows that are too large, too coherent, and too aligned to be easily dismissed. The question is no longer whether bulk flows exist, but what they are telling us about the universe. From the void perspective, the answer is straightforward. We are inside a large-scale outflow driven by an enormous underdense region. The Milky Way's motion is a local expression of a much larger pattern. The cosmic web is not static. Matter is still draining out of voids and piling into walls and nodes, sharpening the contrast between empty and dense regions. In this process, Galaxies acquire velocities that reflect their position within the web. Those velocities carry information about the deepest structures of the universe, including the ones we cannot see directly, because they are defined by what is missing rather than what is present. Seen this way, the anomalous motion of our galaxy is not an embarrassment for cosmology. It is an opportunity. It provides indirect evidence for the reality and influence of cosmic voids on the largest scales. It links local dynamics to global structure, and it reinforces the unsettling idea that our cosmic neighborhood is not typical. We are riding a vast gravitational current shaped by emptiness, carried along by forces that arise from the uneven distribution of matter across billions of light years. Whether the standard model can fully accommodate this picture, or whether it must be revised to account for it more naturally, remains an open question. What is clear is that bulk flows and anomalous velocities are not minor details. They are loud signals in the data, pointing toward a universe whose largest motions may be driven as much by voids as by clusters. The Milky Way is not drifting aimlessly through space. It is moving with purpose, its speed and direction etched by the immense hollow that surrounds us. The implications of these vast motions and coherent flows reach far beyond questions of velocity or structure. They strike at one of the deepest assumptions underlying modern cosmology itself: the cosmological principle. This principle states that the universe, when viewed on sufficiently large scales, is homogeneous and isotropic. In simple terms, it means there is no special place in the universe, no privileged location, no center. The laws of physics and the large-scale properties of the cosmos should look the same from any galaxy, in any direction. This idea has been enormously powerful. It allowed cosmologists to build elegant models of the universe using a small set of parameters, confident that our observations were not fundamentally biased by where we happen to be located. For decades, the cosmological principle has been less a tested law than a guiding assumption, and until recently, it appeared to work remarkably well. The KBC void, however, places that assumption under unprecedented strain. A structure of this size, with this level of underdensity, extending for nearly 1 billion light-years in all directions, makes our position statistically unusual. Not impossible, but rare enough to raise uncomfortable questions. If we truly reside deep inside such a void, then our local environment is not representative of the cosmic average, at least on scales relevant to many of our measurements. The very success of cosmology may have rested on a coincidence of location rather than a universal truth. This does not automatically mean the cosmological principle is false. It means its domain of validity may be more limited than once thought. One line of critique focuses on scale. Defenders of the principle argue that homogeneity does not need to hold at every conceivable size, only beyond some sufficiently large scale. Below that scale, structures like clusters, superclusters, and even large voids are expected. The key question becomes one of measurement. How large is large enough? If homogeneity only emerges beyond 2 or 3 billion light-years, then the KBC void may still be compatible with the principle, even if it complicates our local observations. From this perspective, the problem is not that the universe violates homogeneity, but that we have not yet reached the scale at which homogeneity truly applies. Another critique appeals to the anthropic principle, the idea that our location in the universe is conditioned by the fact that we exist to observe it. In this view, living inside a void may not be surprising at all. Underdense regions offer calmer environments with fewer galaxy collisions, lower radiation backgrounds, and more stable long-term conditions for the formation of complex structures like planetary systems and life. From this angle, our position is not special in a cosmological sense, but selected by necessity. We observe the universe from a void because observers are more likely to arise in such regions. While this argument has philosophical appeal, it is difficult to test and risks sliding into circular reasoning. It explains our location by our existence rather than by physical mechanisms that can be measured independently. Critics also emphasize the uncertainty in defining the void itself. The boundaries of the KBC void are inferred statistically, and its exact shape, depth, and extent depend on how galaxies are counted and weighted. Different surveys use different methods, and while they broadly agree on an underdensity, the precise parameters remain under debate. Some argue that the void is not a single coherent structure, but a patchwork of smaller underdense regions whose combined effect has been overstated. Others suggest that observational biases, such as incomplete sky coverage or subtle selection effects, may exaggerate the appearance of a large void. These are serious concerns, and they highlight the need for caution. Extraordinary claims demand extraordinary evidence. At the same time, the convergence of multiple independent lines of evidence is difficult to ignore. Galaxy counts, bulk flows, peculiar velocities, the Hubble tension, and temperature imprints in the cosmic microwave background all point in a consistent direction. They suggest that our local universe is not perfectly average. Whether this represents a genuine violation of the cosmological principle or a refinement of its scope is still an open question. What is clear is that the principle can no longer be treated as an untouchable axiom. It must be tested, quantified, and possibly revised in light of new data. Cosmology is entering a phase where assumptions long taken for granted are being scrutinized with unprecedented precision. Larger and deeper surveys will map galaxy distributions far beyond our local environment. Improved measurements of cosmic flows will clarify whether the observed motions truly persist on the largest scales. New probes of dark energy and gravity will test whether alternative explanations can account for the anomalies without invoking a special location. Until those investigations are complete, no definitive verdict can be reached. The cosmological principle may survive, albeit in a more nuanced form, or it may yield to a more complex picture of the universe, one where location matters more than we once believed. Either outcome would represent progress. The unsettling possibility raised by the KBC void is not that cosmology has failed, but that it has grown precise enough to reveal its own limits. If the cosmological principle is to be questioned seriously, the evidence cannot rely on a single type of observation. Independent checks are essential, especially ones that probe the universe using entirely different physical mechanisms. Two of the most powerful tools available for this purpose are baryon acoustic oscillations and the cosmic microwave background. Unlike galaxy counts or velocity measurements, these signals are rooted in the early universe itself, long before voids, filaments, or galaxies took shape. That makes them uniquely valuable as cosmic benchmarks. Baryon acoustic oscillations, often shortened to BAO, originate from sound waves that rippled through the hot plasma of the early universe before atoms formed. In that primordial era, matter and radiation were tightly coupled, and pressure waves traveled outward from tiny density fluctuations. When the universe cooled enough for atoms to form, those waves froze in place, imprinting a characteristic separation scale into the distribution of matter. Billions of years later, that scale remains visible as a slight preference for galaxies to be separated by a specific distance. Because this distance is set by well-understood physics, BAO acts like a cosmic ruler, a standard gauge against which the expansion and structure of the universe can be measured. When astronomers apply this ruler locally and compare it to measurements from more distant regions, something intriguing appears. The BAO signal indicates that the density of matter in our local universe is lower than the cosmic average. This is not inferred from counting galaxies directly, but from how the characteristic BAO scale stretches and shifts depending on environment. In regions with less matter, the expansion history differs slightly, and the BAO imprint reflects that difference. Multiple analyses have found that the local BAO measurements are consistent with a significant underdensity extending across large scales, aligning closely with the proposed size and depth of the KBC void. This result is especially compelling because BAO is insensitive to many of the biases that affect galaxy surveys. It does not care how bright galaxies are or how they are selected. It responds to the underlying matter distribution itself. The fact that it points toward a local density deficit strengthens the case that the void is not an artifact of how we observe galaxies, but a genuine feature of the universe. An even more ancient and comprehensive probe comes from the cosmic microwave background, the faint radiation left over from the Big Bang. The CMB provides a snapshot of the universe when it was only about 380,000 years old, long before large-scale structure formed. On its own, the CMB appears remarkably uniform, with temperature variations of only a few parts in 100,000. But as this ancient light travels across the universe toward us, it passes through evolving structures, including clusters, filaments, and voids. These encounters leave subtle secondary imprints on the CMB. One of the most important of these is the integrated Sachs-Wolf effect. As CMB photons pass through regions where gravitational potentials are changing over time, they gain or lose small amounts of energy. In a universe dominated by dark energy, gravitational wells and hills slowly decay as space expands. When light passes through a large void that is expanding, the energy shifts do not perfectly cancel out. The result is a slight cooling of the CMB in the direction of that void. This effect is extremely weak, but it becomes detectable when averaged over large regions of the sky. Observations have revealed correlations between known large voids and small cold spots in the CMB, exactly as predicted by the integrated Sachs-Wolf effect. Among the most famous examples is the so-called cold spot, an unusually large and cold region of the CMB that has puzzled cosmologists for years. While its statistical significance has been debated, its location coincides with an enormous underdense region known as the Eridanus supervoid. This supervoid spans hundreds of millions of light-years and is one of the largest known structures of its kind. The alignment between the cold spot and the Eridanus supervoid is difficult to ignore. While it may not explain the entire temperature anomaly on its own, it demonstrates that voids of sufficient size can leave measurable imprints on the CMB. More broadly, studies correlating galaxy surveys with CMB maps consistently find evidence of the integrated Sachs-Wolf effect at the locations of large voids. These signals are weak but statistically meaningful, and they point in the same direction as other lines of evidence. Taken together, BAO and CMB observations provide powerful, independent confirmation that our local universe is underdense on very large scales. They do not rely on the same assumptions or measurement techniques as galaxy counts or velocity surveys, yet they converge on a similar picture. This convergence does not prove that the KBC void fully resolves every cosmological tension, but it dramatically reduces the likelihood that the idea is a coincidence or an observational illusion. When the universe is interrogated using its oldest light and its most fundamental physical scales, it appears to whisper the same unsettling message. Our cosmic neighborhood is not average, and the emptiness around us has left fingerprints across space and time. When the discussion turns from cosmological parameters and ancient radiation to galaxies themselves, the void takes on a more intimate significance. Voids are not only empty regions that distort measurements and challenge assumptions. They are environments, and like all environments, they shape what forms within them. Galaxies that live inside cosmic voids are not simply smaller versions of those found in dense clusters. They follow different evolutionary paths, governed by isolation, scarcity, and time. Studying them offers a rare opportunity to ask a profound question. Does living inside a vast cosmic emptiness make the universe more or less hospitable to life? Galaxies in voids tend to be small, faint, and widely separated. They are often low-mass systems, with fewer stars and weaker gravitational binding than the grand spirals and ellipticals found in clusters. Because voids lack the dense filaments and nodes of the cosmic web, galaxies there experience far fewer interactions with neighbors. In crowded regions, galaxies constantly tug on one another, collide, merge, and tear material apart through gravitational encounters. These interactions drive rapid evolution. They trigger bursts of star formation, feed central black holes, strip gas, and ultimately transform galaxy shapes. In voids, most of that violence never happens. A void galaxy can go billions of years without a significant encounter. Its evolution is slow, quiet, and remarkably steady. This isolation has important consequences for the internal makeup of void galaxies. Many of them retain large reservoirs of cold hydrogen gas, the raw material for forming new stars. In denser environments, galaxies often lose this gas early, either through collisions or through interactions with hot intracluster plasma. Deprived of fuel, star formation shuts down, and galaxies age rapidly. In voids, the gas remains. Star formation proceeds at a leisurely pace, sometimes continuing steadily for billions of years. This slow burn produces galaxies that are chemically young compared to their cluster counterparts. They tend to have lower metallicities, meaning they contain smaller amounts of heavy elements like carbon, oxygen, iron, and silicon, which are forged in the cores of stars and dispersed through violent stellar deaths. The presence or absence of heavy elements matters deeply when considering the possibility of life. On Earth, virtually everything we associate with biology relies on elements heavier than hydrogen and helium. Rocky planets require silicon, oxygen, iron, and magnesium. Water requires oxygen. Organic molecules require carbon, nitrogen, and phosphorus. These elements are not produced in the Big Bang. They are the products of stellar evolution, supernova explosions, and neutron star mergers. Environments that are poor in heavy elements may struggle to form Earth-like planets at all. This raises an immediate concern about void galaxies. If their chemical enrichment proceeds more slowly, does that make them less hospitable to life? The answer is not straightforward. While void galaxies are metal poor compared to massive cluster galaxies, they are not devoid of heavy elements. Over billions of years, even slow star formation enriches the interstellar medium. Many void galaxies today have metallicities comparable to those of early galaxies in denser regions. This means they can, in principle, form rocky planets, albeit perhaps less frequently or later in cosmic history. Moreover, lower metallicity environments may produce different types of planetary systems. Gas giants may be less common, while smaller rocky worlds could still arise. The diversity of planetary architectures in the universe suggests that life-friendly conditions may not require an exact match to the solar neighborhood. Beyond chemistry, environmental stability plays a critical role. Dense galaxy clusters are hostile places. frequent gravitational encounters can destabilize planetary orbits. Nearby supernovae can bathe planets in lethal radiation. Active galactic nuclei can flood regions with high-energy particles. In contrast, voids are quiet. Galaxies are widely spaced, reducing the likelihood of close encounters that could disrupt star systems. Supernova rates are lower simply because there are fewer massive stars forming at any given time. The background radiation environment is calmer. Over long timescales, this stability could be a significant advantage for the emergence and persistence of complex life. There is also the question of timescales. Life, at least as we understand it, appears to require billions of years to progress from simple chemistry to technological intelligence. Environments that remain stable over such durations may be better suited to this process than ones marked by repeated catastrophic events. Void galaxies, evolving slowly and gently, provide exactly that kind of long-term consistency. Stars in these galaxies can live out their full lifespans without being disturbed by external forces. Planetary systems may remain dynamically stable for tens of billions of years, especially around long-lived, low-mass stars. However, the same factors that promote stability can also hinder progress. Slow star formation means fewer stars overall, and therefore fewer planetary systems. The lower density of galaxies means fewer opportunities for the exchange of material between systems. In denser regions, interstellar objects and enriched gas are more easily shared through interactions and mergers. In voids, each galaxy is largely on its own. This isolation could limit the spread of complex chemistry across systems, potentially slowing the development of life-bearing environments. Another layer of complexity comes from cosmic radiation. While voids are quieter in terms of nearby violent events, they may be more exposed to background radiation from the wider universe. With fewer intervening structures to absorb or deflect high-energy particles, cosmic rays may travel more freely through void regions. The impact of this on planetary atmospheres and biological evolution is still poorly understood. It could be negligible, or it could impose subtle constraints on habitability. The Milky Way's position adds a further twist to the story. Our galaxy resides within the KBC void, but is not a typical void galaxy. It sits on a filament within the void, connected to other structures and enriched by a long history of mergers and interactions. This places us in a hybrid environment. We benefit from relative isolation on the largest scales, reducing exposure to cluster-level violence, while still enjoying the chemical richness and structural complexity provided by filamentary growth. In this sense, our location may represent a compromise between extremes. Not too crowded, not too empty. This perspective feeds back into the anthropic argument raised earlier. Perhaps observers are more likely to arise in regions like ours, on the edges of voids or within underdense filaments, where conditions strike a balance between stability and enrichment. Too dense, and the environment is chaotic and dangerous. Too empty, and the raw materials and interactions needed for complex chemistry are scarce. The universe may naturally produce pockets where these competing factors align, and it is from such pockets that observers look out and attempt to understand the cosmos. From a broader evolutionary standpoint, voids may play a crucial role in the future of life in the universe. As dark energy drives accelerated expansion, galaxies outside our local region will eventually recede beyond the cosmic horizon. Over tens of billions of years, observers in most galaxies will find themselves increasingly isolated, surrounded by darkness. Void galaxies, already accustomed to isolation, may experience this transition less dramatically. Their evolutionary paths may continue relatively undisturbed, long after interactions cease elsewhere. There is also the question of longevity. Low-mass stars, which are abundant in small galaxies, can burn for trillions of years. In void environments, where disruptive events are rare, such stars could host stable planetary systems far into the future. Life, if it arises, could persist on timescales vastly longer than those we associate with cosmic history so far. In this sense, voids may not be cradles of early life, but they could be refugees for its long-term survival. Yet uncertainty remains. Our understanding of life beyond Earth is based on a single example. We do not know how flexible biology is or how dependent it is on specific chemical or environmental conditions. It is entirely possible that life thrives under circumstances we would currently consider hostile or fails to emerge in places we assume are ideal. Void galaxies test the boundaries of those assumptions. They force us to confront the possibility that habitability is not solely a function of local conditions, but of cosmic context. In the end, the question of life in voids mirrors the broader cosmological debate surrounding the KBC void itself. Is emptiness a limitation or an opportunity? Does isolation hinder complexity, or does it protect it? The same void that challenges our measurements and assumptions may also offer environments uniquely suited to certain forms of cosmic evolution. What appears barren on the largest scales may, on smaller ones, be quietly nurturing. The emptiest regions of the universe are not irrelevant backwaters. They are fundamental components of cosmic structure, shaping motion, expansion, and observation. They may also shape the prospects for life itself. As future telescopes probe ever fainter galaxies and characterize planets around distant stars, we may begin to answer these questions with data rather than speculation. Until then, voids remain one of the universe's most intriguing paradoxes, vast realms of near-nothingness that nonetheless influence everything, from the fate of galaxies to the possibility that somewhere, in the quietest corners of the cosmos, life has found a way to endure. When the influence of voids is projected far into the future, the picture becomes even more stark. The same dark energy that already dominates the interior of cosmic voids will continue to assert itself with increasing authority as time passes. Gravity, which once sculpted the cosmic web from tiny fluctuations, will steadily lose its ability to counteract the expansion of space. In dense regions, gravity can still bind galaxies together for long periods, but even those structures are living on borrowed time. Inside voids, where matter is already sparse and gravitational resistance is weak, dark energy faces almost no opposition. The expansion of these regions will not merely continue, it will accelerate. Voids will swell faster than the cosmic average, pushing surrounding filaments and walls farther apart, thinning the web until its strands stretch toward invisibility. Over trillions of years, the universe will become increasingly dominated by emptiness, not just in volume, but in influence. As this process unfolds, the large-scale structure of the universe will undergo a slow but relentless transformation. Galaxies bound together in clusters will remain intact for a time, but everything beyond those gravitationally bound islands will drift away. Filaments connecting clusters will stretch and eventually break as expansion overwhelms their gravitational cohesion. The cosmic web will unravel, not violently, but quietly, thread by thread. From within any given galaxy or small group of galaxies, the universe will appear to be shrinking, not expanding, as more and more distant objects slip beyond the cosmic horizon. This horizon is not a physical wall, but a limit imposed by the finite speed of light and the accelerating expansion of space. Beyond it, events can no longer influence the observer, no matter how much time passes. In this far future, isolation becomes the defining feature of cosmic existence. each gravitationally bound system becomes a self-contained island universe, surrounded by an ever-growing ocean of darkness. For observers living in such a future, the night sky will look profoundly different from ours. Today, even modest telescopes can reveal thousands of galaxies scattered across the sky. In the distant future, all but the nearest galaxies will have vanished from view. Their light will be stretched to wavelengths so long and so faint that it effectively disappears. Eventually, even the cosmic microwave background, the last remaining echo of the Big Bang, will fade beyond detectability. Its photons will be redshifted to wavelengths larger than the observable universe itself, diluted into irrelevance by the relentless expansion of space. This loss carries profound consequences for knowledge. The cosmic microwave background is not just radiation, it is a record. It encodes information about the universe's origin, its early conditions, and the parameters that govern its evolution. Without it, one of the most powerful pillars of cosmological evidence vanishes. Future astronomers, no matter how intelligent or technologically advanced, will face a universe stripped of its historical clues. They will see a small collection of stars and galaxies bound together by gravity, surrounded by infinite darkness. With no visible expansion, no distant galaxies, and no background radiation to hint at a hotter, denser past, the idea of a Big Bang may never arise. Even the evidence encoded in elemental abundances will be ambiguous. The ratios of hydrogen, helium, and lithium, which today provide strong support for Big Bang nucleosynthesis, could be explained in other ways without access to a broader cosmic context. The expansion of the universe itself, once inferred from galaxy redshifts, will no longer be observable. The laws of physics will still operate, stars will still shine, and galaxies will still evolve internally, but the universe will appear static, eternal, and unchanging on the largest scales. Cosmology, as a science of origins and evolution, may become impossible. In such a future, voids will no longer be special regions embedded within a structured universe. They will effectively define the universe. The contrast between dense and empty regions will sharpen until only isolated pockets of matter remain, marooned in an ever-expanding void. The KBC void, once a local anomaly that challenged our assumptions, becomes a preview of the universe's ultimate fate. What we experience now as a bias of perspective will, in time, become the universal condition. Everywhere will resemble a void. Everywhere will be underdense compared to the past. This scenario raises a deeply unsettling implication about our current position in cosmic history. We live at a time when the universe is still readable. The evidence of its origin is still visible. The expansion is measurable. The cosmic web is still intact enough to trace its structure. This window will not remain open indefinitely. In the deep future, the universe will erase the tracks of its own creation. Observers will be trapped inside their local environments, unable to see beyond them, unable to reconstruct the larger story. From their perspective, the universe will seem far smaller, far simpler, and far less dynamic than it truly is. Void domination also reshapes the long-term prospects for life and intelligence. As galaxies become isolated, resources become finite. No new matter will flow in from beyond the local group. Star formation will gradually decline as gas is consumed or locked away in stellar remnants. Over trillions of years, the universe will grow colder and darker. Yet paradoxically, this isolation may also offer stability. With no nearby galaxies to interact with, planetary systems may persist undisturbed for unimaginably long periods. Civilizations that arise in such environments could endure far longer than any we can currently imagine, even as the universe around them grows increasingly empty. Still, their understanding of reality would be fundamentally limited. Without access to evidence of cosmic expansion or origin, future civilizations might construct entirely different cosmologies. They might conclude that the universe is static and eternal, governed by local laws with no beginning and no end. The Big Bang, inflation, dark energy, and the cosmic web would be lost concepts, relics of an era when the universe still allowed itself to be known. In this sense, knowledge of the cosmos is not only constrained by intelligence and technology, but by timing. The dominance of voids in the far future reframes our current debates in a new light. The questions we struggle with today about local bias, cosmic averages, and the validity of the cosmological principle may one day be unanswerable. The universe will not always provide the data needed to test our theories. That it does so now is not guaranteed by any law of physics. It is a temporary condition. We are living during a brief cosmological epoch when the universe is transparent enough to reveal its history and structured enough to betray its underlying order. Seen this way, the void surrounding us is not only a challenge to our measurements, it is a reminder of impermanence. The structures we study, the signals we analyze, and the conclusions we draw are all contingent on a universe that is still young enough to remember its own birth. As dark energy continues to stretch space and voids grow ever larger, that memory will fade. The future universe will be quieter, darker, and far more isolated than the one we inhabit today. And in that future, the Big Bangs will not be a debated theory or a refined model. It will be an unknowable event, erased from observation by the very expansion it set in motion. After tracing the consequences of voids from the earliest moments of the universe to its farthest future, we return to the unsettling realization that began this journey. We are not standing on neutral cosmic ground. We are living inside a vast cosmic whole. This is not a metaphor designed to provoke awe, nor a speculative idea waiting for evidence. It is an observational conclusion drawn from galaxy surveys, cosmic flows, background radiation, and the motion of our own galaxy through space. The emptiness surrounding us is real, measurable, and immense. It shapes what we see, how we measure, and how we interpret the universe. The fact that such a structure exists forces us to confront an uncomfortable truth about knowledge itself. Our understanding of the cosmos is inseparable from where we are embedded within it. For centuries, science has progressed by stripping away the notion that humans occupy a privileged position. Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the center of the universe. Each step displaced us further from the idea of cosmic importance. The cosmological principle emerged as the final expression of that humility, asserting that no location is special and that the universe looks the same from everywhere. The discovery of a vast local void does not return us to an old, human-centered worldview, but it complicates the story. It suggests that while the laws of physics may be universal, the conditions under which we observe them are not. We may not be central, but we may be atypical, and that difference matters. The void challenges the assumption that observation and objectivity can ever be fully separated. We often speak of the universe as if it were a detached object, waiting to be measured from the outside. In reality, we are inside it, immersed in its structures, carried along by its flows, and constrained by its horizons. Every measurement we make is local by necessity. We infer the global from the nearby, trusting that averaging will smooth away peculiarities. But what if the peculiarities extend farther than we assumed? What if the emptiness around us is large enough to bias even our best measurements? The KBC void suggests that this is not a philosophical abstraction, but a concrete possibility. It raises the unsettling idea that some of our deepest conclusions about the universe may reflect our cosmic environment as much as they reflect universal truth. This does not mean that science has failed. On the contrary, it means science is working as it should. The recognition of bias, even cosmic bias, is part of the process of refinement. The void does not invalidate cosmology. It exposes its limits. It reminds us that models are approximations, not mirrors of reality. The standard model of cosmology has been extraordinarily successful, but success does not guarantee completeness. Anomalies are not embarrassments to be hidden. They are signals, invitations to look more closely at the assumptions we no longer question. The void is one such signal, emerging not from speculation, but from the convergence of independent lines of evidence. At a deeper level, the void confronts us with the fragility of universal knowledge. We often assume that the universe is fully knowable in principle, that with enough data and sufficiently powerful theories, its history and structure can be reconstructed from anywhere. The far future of a dark energy-dominated cosmos undermines that assumption. Knowledge depends on access to information, and information depends on light. As expansion accelerates and horizons close, the universe actively erases its own evidence. The fact that future civilizations may never deduce the Big Bang is not a failure of intelligence. It is a consequence of cosmic evolution. The universe does not guarantee transparency. It reveals itself only temporarily. Seen in this light, our position inside a void takes on a new meaning. We are not just spatially isolated. We are temporally fortunate. We exist at a moment when the universe is still legible, when its structure can still be mapped, when its origin can still be inferred. The emptiness around us distorts our measurements, but it also frames our perspective. It reminds us that what we call universal knowledge is always provisional, always shaped by circumstance. Objectivity is not the absence of perspective, but the careful accounting of it. There is also a quiet existential dimension to this realization. The image of humanity lost in a cosmic desert is not meant to inspire despair. Deserts are not empty in the absolute sense. They are places of subtle structure, slow processes, and unexpected resilience. Life on Earth emerged and thrived not because conditions were perfect, but because they were stable enough for complexity to unfold over time. Similarly, the void is not nothingness. It is a dominant feature of the universe, shaping motion, expansion, and possibility. Our presence within it is not a mistake. It is part of the universe's unfolding story. The strangeness of the universe lies not only in its scale or its violence, but in its quietness. Vast regions where almost nothing happens exert enormous influence over everything that does. Emptiness drives motion. Absence shapes destiny. The cosmic desert is not a backdrop. It is an active participant in reality. This inversion of intuition is perhaps the most profound lesson voids offer. We tend to focus on what is present, what is luminous, what is massive. The universe reminds us that what is missing can matter just as much. In the end, the discovery that we live inside a cosmic whole does not diminish humanity's place in the universe. It reframes it. We are observers embedded within structure, trying to understand a whole that we can never step outside of. Our measurements are local, our theories provisional, and our knowledge incomplete. Yet within those constraints, we have managed to uncover astonishing truths. We have mapped the cosmic web, traced the echoes of the Big Bang, and identified the forces shaping the universe's fate. That we can do this at all, from within a vast void in an expanding cosmos, is remarkable. The universe, it turns out, is far stranger than we imagine. Not because it defies logic, but because it refuses simplicity. It is uneven, biased, and contingent. It hides its history as it evolves and challenges us to disentangle perspective from principle. Living in a cosmic whole does not make our quest for understanding meaningless. It makes it more urgent. The desert is vast, the horizon is closing, and the window for knowing is finite. What we choose to learn while the universe is still visible may be the most enduring legacy of our brief moment within the void.